Hi there, welcome to the renal physiology simulation. Here you will learn how a kidney recycles essential nutrients and controls the volume of urine. You have arrived at the perfect time. I just received a call from the hospital regarding a potential new drug candidate for use against hypertension. I was on my way to see a nephrologist to chat about it. Would you like to join me?
Welcome. My name is Dr. Renaz, and I work with patients with high blood pressure. They usually present increased risks of both heart attacks and strokes due to the weakened arteries. Have a look at this scan from one of my patients suffering from kidney disease, very likely caused by his hypertension.
Observe the CT scan and click on the screen to continue.
To treat their condition, we usually use diuretic drugs, compounds that trigger an increased urinary output. Increased production of urine can lead to a decrease in body water content and plasma volume, thus lowering the blood pressure. However, diuretics can have side effects, such as headaches, nausea, excessively low blood pressure, and fatigue. Furthermore, different diuretics work better in different people. This is why we are always looking for more diuretics to broaden the possibilities of treatment. I have one of those new and promising diuretic compounds right here, which was isolated from the leaves of a rare tropical plant. When injected into humans with hypertension, blood pressure was lowered by 20%, and daily urinary output temporarily increased by 15%. However, before we can go into further clinical trials, we really need to uncover the mode of action of this compound, and I would like very much to recruit your help. Here is a vial of the compound, that we're calling Drug X for now. Could you please check if you can figure out how it acts upon the kidney? I have already saved a sample for you.
Click on the sample vial on the desk. Ooh, a mysterious new compound. That's exciting. Alright, we will take the vial and head back to the lab to get started. Pick up a lab coat from the rack. Well done. Now find a glove box and click on it. I see you are now all equipped for lab work. Since Drug X has diuretic properties, it is highly likely that it acts on the kidney. So before we dive into uncovering its mode of action, I think it would be useful to familiarize ourselves again with the structure of the kidney. Move to the hollow table to check out the hollow kidney. Not so long ago, I 3D scanned a mammalian kidney. Go on and explore it. You can choose between 3 different scales using the interface in front of you, and hovering over the different structures will tell you their known functions. Check out the different kidney structures on the hollow table and raise your lab pad when you are done. Click on the lab pad for more information. Are you done studying the kidney structure? Great, let's see how familiar you are with kidney tissues and their functions then. Find the renal artery and click on it. Nice, let's keep going. Where are nephrons located? Don't forget you can always check for the answer on the hollow table. Absolutely. Nephrons extend from the cortex to the medulla, although different structures are present in each tissue. Find the descending limb part of the loop of Henle. Which structure reabsorbs glucose and amino acids, and secretes creatine? That's right, you rock at this. Finally, what are the known functions of the distal convoluted tubule? Awesome! You seem to know your kidney structures very well. That concludes our little crash course, and we can get to work with Drug X now. Know that you can always come back to this hollow table at any point during this simulation if you want to refresh your memory. Alright, let's check out a first possible mechanism for how Drug X can affect urinary output. At the glomerulus, blood is filtered into the proximal tubule. If the rate at which blood is filtered increases, this could increase urine production, and therefore is a possible mechanism of action for Drug X. Look up the glomerulus on the hollow table. A standard way to estimate glomerular filtration rate is to measure the loss of creatinine through urine. Creatinine is a product of skeletal muscle metabolism. Most of it is passively filtered at the glomerulus and is not reabsorbed in the bloodstream, though a small amount is also actively excreted in the proximal tubule. We can calculate the glomerular filtration rate by measuring urinary output as well as the concentration of creatinine in the bloodstream and the urine. However, we will also have to assume that all the creatinine entering the kidney is filtered into the urine in the glomerulus. Let's see if you can do it. Move to the analytical workbench by clicking on it. Turn to the left of the workbench. You can see the table of data on the computer screen, and the equations on the wall. The data comes from the preliminary tests of Drug X as a diuretic from hospital patients, and will help us calculate the glomerular filtration rate in the presence and absence of Drug X. If Drug X is a diuretic that impacts the glomerular filtration rate, what would you expect? That makes sense. An increased glomerular filtration rate would lead to a higher volume of fluid entering the tubule, and ultimately to the secretion of a larger amount of urine, thus a diuretic effect. Let's see if that's what we observe in the data from a hospital patient. With the data and the equations available to you, calculate the glomerular filtration rate before taking Drug X. Nice one. Now let's do it again for the other set of data, after taking Drug X. Now calculate the same glomerular filtration rate, but under the effect of taking Drug X. Correct once again. I will update the table accordingly, and you can see the complete table on the computer screen. Comparing your results between the two experiments, does Drug X affect the glomerular filtration rate? Indeed. So it seems Drug X does not affect the glomerular filtration rate, so that is one possibility we can eliminate for the mode of action. A second hypothesis is that Drug X could also be interfering with the secretion of antidiuretic hormone or the aldosterone hormone, or their respective signaling pathways. Those hormones both act in the kidney, although in different fashions, by promoting higher reabsorption of water and thus a reduced urinary volume, hence the antidiuretic effect. Knowing that ADH and aldosterone are both antidiuretic hormones, which clinical results would be consistent with the hypothesis that Drug X acts to increase urinary output by affecting ADH or aldosterone signaling? Good thinking. Downregulating one or both of the antidiuretic hormones should decrease their effect and thus, increase the urinary output. Unfortunately, results from a recent clinical study suggest that patients receiving Drug X have normal ADH and aldosterone levels, and have normal responses to injection of ADH or aldosterone. Therefore, there is no evidence that Drug X acts by inhibiting either of those two hormones, and we can safely discard this hypothesis from our study. We have now excluded two hypotheses so far. 1. That Drug X affects glomerular filtration. 2. That Drug X affects antidiuretic hormones. I have another suggestion for us to test. Taking a different approach, many diuretics act by affecting the reabsorption of salts in the renal nephron. Testing humans is complicated, but we can do this with a rat right here in the lab using a perfused tubule preparation. We have all the necessary material here, so I suggest we try this out next. Move to the dissection workbench by clicking on it. I have a rat here that was humanely euthanized, so you do not need to worry about this part. I will guide you step by step through the dissection of the relevant structure from the nephron and setting up the reabsorption experiment. We first need to dissect the rat and find the kidneys in the abdomen. Pick up the scalpel on the workbench. Dissect the rat. After putting down the scalpel, cannulate the kidney inside the rat. Good. Using this cannula I perfused the kidney with a saline solution containing collagenase, which disrupts the extracellular walls and will allow us to extract the nephron from the rest of the kidney. Next we are going to perform a coronal section of the kidney to get access to the nephrons. Perform a coronal section using a scalpel, and watch the outcome on the screen. Now we need to dip this coronal section into cold collagenase containing dissection saline. Once again, the collagenase will help break down the tissues by disrupting the extracellular matrix so we can isolate a nephron from the medulla and the cortex. The buffer composition will also help stabilize the cells to keep them intact as much as possible. Using the scalpel, transfer your coronal section to the saline bath in the petri dish. You can see a microscope image of the coronal section on the computer screen. For the next steps, we will need to use micromanipulators under the microscope as the operation is quite delicate. You can see the manipulators and the pipettes above the microscope plate, below the objectives. Place the petri dish with the coronal section under the microscope. Watch the 2D section with the nephron on the screen in the center of the workbench. Many diuretics target the reabsorption of sodium in the body, as reduced sodium retention would mean lower water retention, thus increasing urinary output. Sodium reabsorption occurs in different sections of the nephron, including the thick ascending limb we are now going to dissect. On the screen, click to select the two locations to cut to isolate the thick ascending limb. On the screen, click to select the two locations to cut to isolate the thick ascending limb. Excellent. This is indeed the location of the thick ascending limb. Let me cut it out for you using the microscope as it is a delicate operation. Alright, we have now cut the relevant piece of renal tubule for our experiment. Now insert pipettes into both ends of the tubule by clicking on the micromanipulators. Watch the 2D animation on the screen to understand the flow of perfusate. Raise the lab pad when you are done. Are you done watching the animation? What we are going to measure is the volume of reabsorbed fluid through the tubule. In short, we will perfuse one end of the tubule with the perfusate saline, and measure the resulting volume collected at the other end. The difference will tell us how much volume the perfusate has lost while traveling through the tubule due to being reabsorbed by the epithelial walls. In theory, we can calculate the volume reabsorbed through the walls of the tubule using the following formula: volume reabsorbed equals volume entering the tubule minus volume leaving the tubule. We will measure the volume of fluid leaving through the sides of the perfused tubule, theoretically being reabsorbed in the body, during the time it takes for 1 nanoliter of fluid to accumulate in the collection pipette. In real life, the collection pipette is filled with a light red dyed oil, so it will be easy to see the meniscus marking the division between the oil and the perfused saline coming out of the tubule. Click on the bottle of tritium methoxyinulin to learn more about the perfusate. The saline entering the tubule will contain tritium methoxyinulin. Methoxyinulin is a plant-derived non-metabolizable sugar that is not transported by animal epithelia, so it will remain in the perfused fluid, and will not be reabsorbed. It has been made radioactive by combining it with tritium, which means that its concentration can be measured easily in very small concentrations. This way, by measuring the radioactivity of the perfusate in the collection tube, we can measure the concentration of methoxyinulin and thus deduce the amount of volume reabsorbed by the tubule. Set up a syringe with our saline solution to start our reabsorption experiment. Pick a syringe full of saline and set it up on the microscope. I have now injected the saline with radioactive methoxyinulin into the tubule using the micromanipulators. Once 1 nanoliter of perfusate has been accumulated in the collection pipette, you will need to remove the pipette to measure the concentration of methoxyinulin. Remove the collecting pipette from the microscope and add a rubber bulb. Now you can transfer the perfusate to the vial on the workbench. Bring the vial to the analytical workbench. To measure radioactivity, we first need to mix our perfusate with a scintillation cocktail, which includes scintillator molecules. The radioactivity emitted by the methoxyinulin in the perfluorescate will excite those scintillators, which will in turn re-emit photons we can detect. Holding the vial, add the scintillation cocktail mix. These photons from the scintillator molecules can be counted using a liquid scintillation counter. The data provides us with an indirect measurement of the radioactivity, and thus the concentration of methoxyinulin in our perfluorescate sample. Place the vial in the scintillation counter. Now start measuring the radioactivity by pressing the Start button. Great! We have now measured the radioactivity of our perfluorescate sample. This will be our control in the absence of drug X. Let's use our radioactivity data to calculate the amount of fluid reabsorbed by the renal tubule. Look at the screens to the left of the workbench. We are going to fill in this table for the control experiment. Use the formulae to calculate the flow rate of perfluorescate in the tubule and the amount of fluid reabsorbed. The collected fluid that exited the tubule had 2000 counts per minute of methoxyinulin. Using the formulae on the screen and the calculator, what was the flow rate of the perfluorescate into the tubule and the amount of fluid reabsorbed? That's right. The entering flow rate of perfluorescate inside the tubule was twice the rate at which it was collected in the collection tube, which means half of the perfluorescate was reabsorbed through the walls of the tubule. Now, let's see if the process of reabsorption is active. It could just be that the fluid is leaking out of the tubule via a rip or a bad seal between the pipette and the tubule, or the methoxyinulin is being concentrated by an osmotic effect. For example, the osmotic pressure in the bathing saline might be higher than in the perfluorescate saline, triggering water to leave the tubule through simple diffusion. If the reabsorption process is indeed passive and due to higher osmotic pressure in the external saline, what would be your prediction for the volume reabsorbed in the absence of oxygen to make ATP? Good job! If the reabsorption is driven by passive processes such as osmotic pressure, the volume of reabsorbed fluid should be the same in the presence or absence of oxygen. Here are the results when the tubule is deprived of oxygen. V out equals 2 and C out equals 1000. So V in equals 2 times 1000 divided by 1000 equals 2 and R equals 2 minus 2 equals 0. So, with no oxygen present, no fluid is reabsorbed, which suggests that the reabsorption is active. It also means we still have work to do to uncover the full mode of action of drug X. Here is a model for the ion transport process in the thick ascending limb of the nephron, based on prior research and experiments. Have a look around to learn about the different processes and where drug X could be interfering. As you can see, there are many possible sites of action for drug X. It may not even target any of these known sites. It seems the first thing we have to do is to check if drug X affects reabsorption when applied to either the apical or basolateral side. We'll perfuse using the exact same saline, but include drug X in either the perfluorescate or bathing saline. I will run the experiments by changing the saline myself to save some time. Okay, I have run the experiments and measured the concentrations of methoxyinulin in the perfluorescate after applying drug X in the perfluorescate or in the bathing saline. I have updated the table on the screen on the analytical workbench. Now your job is to finish filling this table with your calculations. Fill the equation on the screen to calculate the reabsorbed fluid rate for the basolateral side. Well done! We can see a difference here, with a reduced reabsorbed fluid rate. Indeed, as you might have noticed, our experimental values were similar to our negative control without drug X, and we logically deduced the same V in and reabsorbed fluid rate R. Great! Now the table is complete. I will leave it up for you to make your own conclusions. What findings can you draw from these data? Great, we are starting to narrow things down. On the apical side, it looks like drug X could potentially block ion reabsorption either by inhibiting sodium reabsorption via the paracellular route, or by blocking the sodium-potassium 2-chloride transporter. We can assess which of these routes is blocked by selectively removing just sodium or both potassium and chloride from the perfluorescate. To remove sodium or potassium, we replace them with choline, a positively charged organic ion that cannot utilize either of these transport methods. To replace chloride, we use gluconate, a negatively charged organic ion. What experimental result would be consistent with drug X acting by blocking the paracellular sodium route? You can use the poster on the wall for clues. It sounds correct to me. While you were thinking about it, I ran the experiments with all the different perfluorescates in saline baths. See what data you can extract out of it. It also seems you know the equation to calculate the reabsorbed fluid rate R now, so to save time I have processed the data myself and filled the remaining columns on the table. Have a look. So finally, what do you conclude from these data? Have a look on the screen to check the ion transport model to help you. Indeed, it seems the diuretic action of drug X has been nullified for each situation when we replaced an ion with an organic ion, whether it was sodium, potassium or chloride. This would suggest the action of drug X depends on the presence of all three ions, which points to the sodium-potassium 2-chloride transporter. So after all our experiments on the influence of drug X on the glomerular filtration, on the levels of diuretic and antidiuretic hormones and on the epithelial transport of the thick ascending limb, how do you think drug X causes a diuretic effect? I believe you are correct, and we now have the experimental data to support this. You did a great job today. Let's announce our results to the nephrologist at the hospital.
You're back. To be honest, I was quite impatient to hear about your findings. So according to your studies, drug X would be blocking sodium, potassium and chloride reabsorption on the apical side of thick ascending limb of the nephron. Logically, water would then remain in the tubule leading to the collecting duct and later to the bladder, which would explain the diuretic effect. How interesting. Thank you very much for finding that out. Now that we know more about the mode of action of drug X, we can properly plan the first stage of clinical studies in humans. Who knows, if everything goes well, we might have a new treatment against hypertension in a few years, and that would also be thanks to you and your work today.
Congratulations, you have completed the simulation. We hope you enjoyed it and you feel wiser now.